Okay, today I'm substituting in for Dr. Lee. I am Michelangelo, the best Teenage Mutant Ninja Turtle, and we're going to be playing some games with trig functions. I want to show you something really bizarre that comes up a lot in some of these sections that you'll be doing. So first of all, I'd like to just plot. Let's turn that into a input cell. So I'd like to plot sine of x. And let's let x go from minus pi to pi. There we go. Now I actually want the graph to be sized, the aspect ratio to be true. So, but it's not true that you say aspect ratio. It's automatic, and then it will. So now, if you'll look, the from minus pi to pi is a good deal longer than the minus 1 to 1. Now let's remind ourselves what arcsine looks like to that. So let's throw in there arcsine or sine inverse. Arcsine. So the maroon one is the arcsine, and notice that it goes up to from minus 1 to 1, so that's the domain of arcsine. While the domain of sine is all real numbers, the domain of arcsine is just minus 1 and 1. Why? Because arcsine is the inverse of sine, so its domain is the range of sine, and it goes from minus pi to pi. Well, if you think about it, arcsine can give back all sorts of angles. There's lots and lots. There's an infinite number of angles that will give you each of the numbers between minus 1 and 1. So when we define arcsine, we define what's called the principal branch, which means that we define what angles it's going to give back. And normally we assume that arcsine gives back from minus pi over 2 to pi over 2. Now this comes to play in lots of ways. Let's say we were taking the arcsine up again. We want to. Let's suppose we are taking, let me scroll this up a little, the arcsine of the sine of, now what do we take the sine of? We take the sine of angle. So we've got some angle, we take the sine of it, then we take the arcsine of it, we would think it would give back the angle. And now let's go the other way. Let's take the arcsine, and what do we take arcsines of? Well, ratios of two sides of a right triangle. So we'll take the arcsine of some ratio, and we'll take the sine of that, because that ratio will give back an angle. The arcsine of that ratio will give back an angle, and then the sine of that should maybe give back the ratio. Let's see what Mathematica does with each of those. Well, with the second one, Mathematica says, hey, I know what that is. Those are inverses of each other. Boom. I'll give you back the ratio you started with. Why is that? Well, when arcsine gives back an angle, no matter what angle it is, it's the angle. It's one of the many angles that sine of will give you back the ratio. So it doesn't have any problem knowing which one to hand back on this. But up here, if I take the sine of an angle, I get a ratio. But there's lots of different angles. This could be this could come out to be 0, and you still don't know which angle it is. So the sine of lots of different angles would give you 0. So the arcsine of 0 should be what? It doesn't know. It can't give me back that angle. So it leaves it that way. What I could do is ask it to simplify itself, but I'll do it in a certain way. It's called refine, where you make some assumptions. I want you to refine that with making the assumption that angle is going to be between minus pi over 2 and pi over 2. So if you'll look, that's from here to here, and sine's 1 to 1 on that. So we'll go pi over 2. Let's make that minus pi over 2. So we're going to refine this, assuming that the angle is between minus pi over 2 and, let's say, less than or equal to pi over 2. And see what we get. Now it gives us back that angle because it knows that there's only one angle for each ratio. There's a 1 to 1 correspondence between those, and so it knows what to do with the arcsine. Now, so here we looked at this, but what about if you took some other trig function applied to arcsine? Because arcsine, you apply it to a ratio, back comes some angle, and then you could take some other trig function of that angle. Would we know anything about it? For instance, let's say we take the cosine, we'll go back to this. Let's say, let me scroll up a little bit. Let's say we take the cosine of the sine inverse of some ratio. So we take a ratio, we take the arc sine, the inverse sine of that, to get back some angle, and then we take the cosine of that angle, not the sine. What does Mathematica say about that? Will it give me back x? I doubt it, right? So what will it give me back? That's stunning, right? Wrong way. I should point that way. That's stunning, right? So what happened here? Well, before I say anything, let me point out it gets even more bizarre. It can, let's say we take the tangent of that, right? Let's say we take the secant of that. Okay. Now, there's enough there that should let you know that Pythagorean theorem is involved. At this point in your mathematical career, anytime you see some squares and ones and things like that and square roots, you should think circles are involved, Pythagorean theorem is involved. That's what you should think, okay? So what do we have? How do we get this? Well, what I want to do is go back to the one of the many Pythagorean identities. So let's actually, let's go back to this. Let's go into here. So we've got sine of x squared plus, let's come down, plus cosine of x squared equals 1. I really should just write this like equals 1 and write this like a textbook would, or kind of. Okay, now what if that's true for all values x. So what if we stuck in there some value that we get an arc sine of some ratio? So let's, instead of x, let's put in arc sine of x. That's going to be some number, whatever x is, arc sine of it will give me back some number. So let's put arc sine of x. Now right off the bat, sine of arc sine of x, as we saw earlier, is well defined. As long as you're putting in an x that's in the domain of arc sine, you're good to go. So this whole thing becomes just x, right? And then if we pull this over to the other side, we get minus x squared. Now we see automatically that there's actually restrictions on what x can be, because it's square subtracted from 1 has got to be positive because or non-negative because it's set equal to something that's a square of a number, right? It becomes even more clear if we take the square root of both sides, the positive square root of both sides, or you can think of plus and minus the square root of both sides. But right here I'm going to take the positive, and then you might on your own time think about why are we choosing the positive root. Boom. And we've got the cosine of arc sine of x is square root of 1 minus x squared. Now what about cosecant? What about secant? Well, 1 over cosine. So if I put this over, if I put 1 over this, I would have the same thing as secant of arc sine of x, which would be 1 over this. If I looked at sine of arc sine of x over cosine of arc sine of x, that would be tangent of arc sine of x, which would be what? X over this. So all the different things, all the different trig functions you can apply to arc sine, all the different trig functions you could apply to any other inverse trig function is going to give you something very much non-trig-like, which tells you that when you're doing integrals and derivatives of things that have this stuff in it, it might actually end up involving trig functions at the end of the game when you're finding the solution, okay? So this game basically is to kind of inform you of where do all these square roots of 1 minus x squares and 1 plus x squares and things like that are popping up in the work that follows from here. Okay? Beautiful stuff. Hope that helps.